Good morning, everyone. So, Saleh, Kevin, can you see my screen?
Yes, sir.
Okay. Okay, so last time we talked about the assignment problem, which is a prototype model in the linear programming problem, and the goal is to assign a number of the resources, usually workers or the machines, to an equal number of activities. So usually it's going to be the jobs, right? While minimizing the total cost of allocation. So, and actually the assignment problem is a special case of the transportation problem. So actually we can use we can solve the assignment problem directly as a regular transportation problem, but the fact that all of the supply amount and the demand amount equals 1 in the assignment problem has led to the development of the streamlined version of the solution algorithm, which is called Hungarian method that we discussed last time. So today I'm going to continue to talk about the assignment problem and the transportation problem with an example problem. Okay. So these are the general formulation of the assignment problem. You know, we have 2 sets of constraint sets, right? And this screen just summarize the Hungarian algorithm. So let's take an example for the assignment problem first, okay? And then later on, we're going to give you another example for the transportation problem. Okay, so let's imagine that you are working for a major US airline company as an operations research analyst. Okay, so let's suppose your boss came in earlier today and asked you to develop a crew scheduling. So basically, your boss wants to know how to effectively assign the flights to the crews to minimize the total layover time. Okay, so that's the main goal. He wants to minimize the total layover time between the 2 airline schedules. So here's the summary information that your boss provided. And as it can be seen here, an airline operates 7 different flights daily between New York City and Chicago. Okay, and the crews are based in either city and fly to and from the other city each day. Okay, so these are the basic rules. And also we need to consider the following restrictions. So let me read through them. So first, each of the airlines crews live either in Chicago or in New York City. And each day, the crew must fly one New York to Chicago flight and one Chicago to New York flight. Okay? And there must be at least 1 hour layover time between flights. And at the end of the day, the crew must be in its hometown, okay, home city. So the airline wants to assign the flights to these crews to minimize the total layover time. Okay, that's our goal. So they want to know how many crews should be based in each city. Okay, so the key point is that the airline wants to minimize the total layover time. Just keep in mind that. So intuitively, we need to make a table of the layover times for the flight pairs, right? So here, based on the given information, we made a table just like this that shows a layover time for the flight pairs. Okay? So in this table, this portion, these pairs flown by a Chicago-based crew. Okay? So for example, this number 8 represents the layover time for the Chicago-based crew, right? So he basically takes flight number 1 to New York City. So he will arrive New York City at 10 o'clock in the morning, right? And then he takes flight number 7, right? He takes flight number 7 at 6 p.m. to come back to Chicago. So in this case, the layover time would be 8 hours. Does that make sense? So 10 a.m. to 6 p.m. The difference is 8 hours. That's why I put number 8 down here. Why don't you take another example? So this number 3 represents again the layover time for the Chicago-based crew. So he or she takes flight number 2 to New York City, right? So he will arrive New York City at 1 o'clock in the afternoon. And then he will take flight number 6 at 4 o'clock in the afternoon to come back to Chicago. So in this case, the layover time becomes 3 hours. So likewise, for all the other cells in this area, we can compute the layover times. Does that make sense? Okay. Any questions so far?
I'm good.
Okay. Let's move on to the next screen. And so, likewise, these pairs flown by a New York City-based crew. Okay. Then how do you get this layover time of 2 hours in this case? By the way, what happened if this is the case of the Chicago-based crew, not the New York City-based crew? If the crew is based on the Chicago, then he takes flight number 3 to New York City, right? So he will arrive New York at 4 p.m., right? And then he will take flight number 2 at 4 o'clock the next day in the morning, right? And actually, this violates the restrictions that each day a crew must fly one New York to Chicago and one Chicago to New York flight. And it also violates the restriction, another restriction that at the end of the day, a crew must be in his home city. Okay, so of course, in this case, this value 2 cannot be obtained. So this must be the case of New York-based crew. Okay. So if this is the New York-based crew, then he takes flight number 2 to Chicago first, right? So he will arrive in Chicago at 10 o'clock in the morning, and then he will take flight number 3 at noon, right? To come back to New York City. So in this case, the layover time becomes 2 hours. Okay. So this must be based on the New York City-based crew, not the Chicago-based crew. Okay, does that make sense? Okay, now let's try this number. Okay, so the crew takes flight number 3 to Chicago, right? And then he will arrive Chicago at noon, right? And then he will take flight number 7 at 8 o'clock at night to come back to New York City. So in this case, the layover time becomes 8 hours. That's a long period of time, right? So likewise, you could obtain layover times for the rest of the stars in this area. Okay. Any questions so far? So obviously, before you implement this this matrix, layover time matrix, for the assignment problem, so that we can use the Hungarian algorithm, but you have to fully understand how to get each individual values in this table, right? That's why I want to go through some of them. Okay. Okay. So next is okay. These pairs in these areas are impossible. Yeah. Okay. It's invisible. So for example, if this is the case of Chicago-based crew, then what's happened? He arrives New York City at 1 p.m. through flight number 2, right? And then he's supposed to take flight number 3 the next day at 10 o'clock in the morning to come back to Chicago. Again, this violates these 2 conditions, right? Each day, the crew must fly 1 New York to Chicago and 1 Chicago to New York flight. And also at the end of the day, crew must be in his home city. So this is not the Chicago-based crew, right? Then what if it's based on the New York City? In that case, he arrives Chicago at noon through flight number 3, and then he's supposed to take flight number 2 the next day at 9 o'clock in the morning to come back to New York City, right? Again, this violates these 2 conditions. So obviously, this cannot be the New York-based crew either. Okay, so that's why this is impossible to happen. So So let's implement Hungarian algorithm that we discussed last time to this labor time matrix. Okay, so we can consider this as the cost matrix because your boss wants to minimize the total labor time. So we can easily use this table, right, for the assignment problem, the Hungarian. So let's do that. So I'm going to use the Excel spreadsheet just like we did last time. So let me make 7x7 matrix first. Okay, so this is the matrix that I have. So just let you know, I put this large number compared to relatively much big number here to make sure these pairs never be used. Okay. So we are going to use this cost matrix for the Hungarian average. Okay. So obviously this is the 7x7 matrix. So we don't need to do the step number 0 because it's already have the standard form, right? So we can safely move to the step number 1, the row reduction. So I'm gonna get the minimum value for each row. This minimum in this, right? I'm gonna get the minimum value for each row. And then I'm gonna copy. And then I'm going to subtract this minimum value from each component. So that's going to be this value minus this. Okay. Yes. So now we need to perform the column reduction. So let me copy this. Then again, I'm going to identify the minimum numbers in each column. Okay, here. I'm going to subtract the number from each column. Yes. Okay, so now we've done the both row and column reductions, right? So what's the next step? We need to identify the minimum number of lines that can cover every zero in this cost matrix. Okay. So how many lines we need to draw? So I'm gonna draw this 1, 2, and 3, 4, 5. Okay. So obviously 5 line can cover every zero. We don't even need 7 different lines to do this. Mark it. Yes. So I'm going to copy this. This line because I want to identify the minimum aligned cost. Okay. Yeah. Minimum aligned cost. How much is that? The minimum value among these areas will be 2, right? Right here. So we are doing step number 4 right now, right? We identify the smallest aligned cost, and then we are going to subtract this cost from all aligned cost, and then add the same cost at the intersection of the lines. That's what you're going to do. Okay, so you can do this when you want. So what I'm going to do is subtract this minimum number 2 from this area, right? So I'm going to do the same thing here. And here as well. Right? And this. Okay. And I'm going to add this minimum aligned cost to the intersection of these 5 lines, which are right here, right? I'm going to add the same amount. E plus 50. Okay. And then this part is same as before, right? So I'm gonna just copy from previous matrix. Sure. Okay. Okay. Now, what you need to do is go back to step number 3 again. Because we don't need the row and column reduction anymore. Because each rows and columns in this updated cost matrix, there is at least 1 0, right? So the row reduction and column reductions not necessary. So you need to find the minimum number of lines that can cover every zeros. Okay. So this time I'm going to draw this 1 line, 2 lines, 3, 4, 5. Okay. So again, 5 lines can cover every zeros in this reduced cost matrix. And again, I need to find the minimum line cost. That simply I can graph those areas. Again, the minimum line cost is 2. This is right here, right? So I'm going to subtract the cost of 2 from this location, align the area, and then add the same amount to the intersection of these 5 lines. That's what I'm going to do. So here I'm going to subtract 2. Simple polygon. These are the intersection area, right? So I'm going to add the same cost. Okay. Yeah. Then these areas remains the same. Okay. Now, how many lines do we need to cover every zero? This we just lay over time matrix. So row 1, 2, 3, 4, 5, and 6. So we do need 6 lines. That's right. We don't need the 7 lines to cover every zero. Now again, we need to identify the minimum line cost. That's going to be minimum values on this part, right? Again, it's going to be 2. So I'm going to subtract 2 from this area. and the intersection of the lines. Okay, I'm going to add the same amount. Plus 2. Okay, and then all of these areas remains the same. I'm going to copy same value. Matrix. Okay. Now again, we need to find the minimum online cost. What is that? First, yeah. So the minimum online cost would be again. Okay. Oh, I see. Okay. We need to find the minimum number of lines again, right? To cover every zero values here first, before we identify the minimum line cost. So row 1 line, 2 lines, 3, 4, 5, and 6. I'm going to draw 6 lines. Yes. Okay. Now we can identify the minimum line cost. That's going to be 2. Okay. Next table, we're going to have a lot more zeros. Yeah, right? So we are going to subtract cost from here. And add the same amount right here, right? This value plus 2. And then the remain the same, right? Let's copy from the previous matrix. Okay, now we have the updated table like that. Okay, now again, let's find the minimum number of lines that can cover every zero values. So 1, 2, 3, 4, 5, 6, 7, Okay. So obviously, we do need 7 lines. Okay. So the total number of lines, minimum number of lines, cover 0. It will be 7. And this number 7 is exactly same as the total number of rows for the columns. So 7, right? So this implies that we should be able to have the 0 cost assignment based on this updated table. So we're going to stop implementing the Hungarian algorithm. And then now we are going to find the 0 cost assignment. Okay. So let me copy this table. I'm going to do the 0 cost assignment based on this. So first of all, you need to choose this because this is the only 0 in the first row, right? So I'm going to choose this. And then mark this with dark color to prevent from the further assignment in the same row, same column. Okay. And again, you have to choose this because this is the only 0 in the last column, right? Then mark it with black. And looks like we are going to have multiple optimal solutions. Because every rows and columns has multiple 0 values. So if this happens, then just arbitrarily choose 1 0. Okay. So I'm gonna choose this 0. And again, there's time. So I'm gonna choose this. And again, we have time. So choose this. And again, we have time. So let me choose this. One left. Choose this. Okay. So now you need to look at this original table. Okay? And then we're gonna have this optimal assignment based on our this selection is based on what it is. Yeah. Okay. So what is the total available time for this assignment? Total available time be the summation of these 7 numbers. It's going to be 25 hours, the minimum layover time that you can achieve with this crew schedule. Okay. Okay, so any questions on this example? So you can see here, as an industrial engineer, especially as the operations research analyst, you can contribute to the airline company, especially for the scheduling portion. Okay, this is just one of the example that how you can contribute to major the U.S. airline. Of course, you can do a lot of different types of scheduling problems, right? For example, for the hospital, you can do the similar type of scheduling. For the outpatient scheduling and operating room scheduling, you just name it, okay? Okay, so let's move on to the next example. Okay. So this example is for the transportation problem modeling. Earlier, I mentioned that some of the important applications of the transportation modeling actually nothing to do with the transportation. So, but actually, this is somehow related to the transportation, transporting the goods. So, I believe this is another good example for the transportation modeling. So let me give you a couple minutes. Why don't you read through the problem description and then try to construct the parameter table for the transportation modeling. Okay, I will get back to you. So let me pause the recording and then get back to you in like 3 minutes. Okay. Okay, so this is the parameter table that I'm going to complete. Okay. So here it does say unit manufacturing cost of the first product would be $31, $29, $32, $28, $29 in plant number 1. So all of these 5 values goes here, right? Come in here, 31, 29, 32, 28, and 29. And likewise, all of these 5 numbers goes to the next column, right? 45, 41, 46, 42, and 43. And here, the unit manufacturing cost of the third product would be 38, 35, 40. In plant number 1, 2, 3, right? Yes. But plant number 4 and 5 do not have the capability for producing this product number 3. Okay, so in this case, how do you handle this issue? What number would you put in here? I'd put, for example, capital M stands for the suitably big number. Okay. If you want, you can put P stands for the big number. So actually, for the Lindo or Lingo input, you might want to input like 1 million, for example, which is relatively a lot larger than the other cost values here. Okay, making sure that this pair will not be used at all. Okay. Okay. Now, how do you put the demand and supply amount? So here, sales forecast indicate that 600,000 and 800 units of products 1 to 3 should be produced. Okay. So that 3 numbers was here 600,000 and 800, right? And lastly, there's 5 numbers goes to here, supply amount, right? 600, 400, 600, 1,000. Okay, so it looks like we've completed the parameter table for the transportation problem. This case, okay. So once you complete this parameter table, the rest of steps are very easy. You're gonna formulate the transportation problem based on this information, and then use Lindo or Lingo to get the optimal solution. So, okay, it's 11, 25. We still have some time, so let's do that. Okay. I'm going to open up the Lindo, Lingo. Lingo. This is Lingo. I'm going to use Lingo. Want to minimize the total cost, right? We are going to use all of these values, right? 5 by 3. Values. That's going to be 31 at 1, 45 x 1, 2, 48 x 1, 3. Plus 29 x 21, 41 x 22, 35 x 3 minus 32 x 1 46 x 2 x 41 42 x 42 and this big number and x 43 29 x 51 42 x 52 x 5. Okay, that's our objective function. Oh, the lingo does need equal sign, right? Don't forget the semicolon for the input constraint size. So we do need two sets of constraints for the transportation problem. Supply constraint and demand constraint, right? So that's going to be first supply constraint. One, two, three. First 600. That's our second supply constraint. For point number 2. Three, 400, next 41, 42, 43. $600. Next 51, next 52, next 53. First. Now we move on to the demand constraint. So we do need 3 constraints for that, right? And for each product. So first one, X. 1, x31, x41, x51 be greater than equals 600. So our first demand constraint for product number 1, x12, x22, x32, x42, x52. Greater than equal to 1000. X now we complete x23, x23, x5 3 greater than equal to 300. That's it. Oh, okay. We forgot to put asterisk as the product symbol for lingo. Come in here. Window doesn't need it, but lingo does it. It should be okay. Okay, we got the optimal solution. Here's the optimal objective function value. That is the minimum cost. 88,400. And these are the optimal solutions. Okay. Okay, so any questions for these two example problems? Okay. Okay, so if you don't have any questions, then this is going to be all for today. And from next week, we are going to talk about the new topic, project scheduling. Okay, so we are going to talk about the critical task method for the project scheduling. Okay.
Thank you so much.
Okay. So I will see you next week then. Thank you so much. Bye-bye.
Thank you.
Thank you.